Okay, so what have we done so far? We have first converted our movie into a vector representation. In this case, we use tags, so how often a movie was tagged with a given category. And then we normalized the length of the vector. The next question, and that's what's going to be interesting for all these recommendations, is how do we find similarities between two items? So here between two movies, but the same principle is applied to anything else, images, books, and so on. So now you might think, okay, I could use similarity as looking what's the distance between two items. So if two items have a big distance, then they are not so similar. And if two items are very close to each other, then they are more similar. That would be a possibility. That's what's called the Euclidean distance. But in general, this is not the best way for finding the similarity in the vector space. So in this example here, we are looking at vectors representing documents, text, like a post or a news item. And we want to find out which ones are similar. So if you look at the distance between the one here, rich, poor, and the three entries, ranks of starring poets well, rich, poor, gap grows, record baseball salaries in 2010. And you want to say which one is most similar based on the distance, then you can see, well, in terms of distance, probably these two here are the closest, and this is the furthest away. But if you look at what you would choose as the most similar item, you would probably say this one here is the most similar one. So if you think about what else you could use instead of the distance in the vector space, you would probably at one point come to the idea that you could look at the angle between the different vectors. So you have an angle between these two, an angle between these two, and these two here as well. And this is what is generally used as the similarity in a vector space. So in terms of the angle, the smaller the angle, the more similar two items are. And in practice, what we do to compute the similarity is, instead of using the angle directly, we are looking at the cosine of the angle. Why? Well, if you remember how the cosine function looks like between 0 and 90 degrees, it's monotonically decreasing. So if the angle is 0, the cosine of 0 is 1. And if the angle is 90, the cosine of 90 is 0. So what we now end up with is a similarity measure between 0 and 1, where 0 means two items are not similar at all. So if two vectors have a 90-degree angle, it means they have nothing in common. And then the angle between these two vectors would be 90 degrees, and the cosine would be 0. On the other hand, if two vectors are identical, then they represent identical content, at least as measured in this vector space. Then the angle is 0, and the cosine of the angle is 1. So now the similarity that we're going to use is the so-called cosine similarity. And the nice thing about the cosine similarity is that it's very easy to compute, because if the vectors are already normalized, this is simply the dot product of the vectors. So you compute the sum of the product of all the individual vector elements. So to see how this works, there is another task on the worksheet. So based on the vectors that you just computed here, the normalized vectors, you can just compute the dot product between two movies to get the similarity between them. So you can fill in this table here to say how similar are two movies in this case. And you can see this is already what you need for an item-to-item recommendation engine, because let's say you bought movie 2. Now you can compute which other movies are more similar to this movie 2, and then you can start recommending them. Maybe you filter out the ones that somebody has already bought or watched before, but then you are left with the ones that are the most similar recommendation. So have fun filling out the table, and I'll see you again in the next lecture part.